As I recall, we had made a command level decision to install the Doka motor with a growl in it.
That's right.
And some ass clown, I guess me, decided that it would be better to see what was inside. Like a little kid, I wanted to see the pieces. Bill has been getting to be quite adroit at taking apart and putting together the gear drive part for the Quaif. And so I've asked him, despite some fear on both of our part, to take more things apart. And you got entirely carried away this time.
I did, yep.
And we took a drive unit that had a good motor, but an inverter that was very low power.
Yeah.
I'm not sure if it was software or sensors. I'm not sure what the problem was.
It wouldn't spin much past creep or something, isn't that right? Yeah.
And it was like being in reverse, even in forward. And the inverter off of our growler and put them together, and this is the result. And that worked out pretty well. Let's fire it up so others may see.
I'm going to hold it down this time.
Our mayhem. And I'd like you to hold it down.
Yeah.
That's so quiet, I can't tell it's working. Is it spinning?
You're going to have to take our word for it.
No, let's spin it up some.
All right.
Hang on. Watch this shit. And we have regen. That got you.
It did. It's surprising.
Lots of power,
Yeah.
but it's so quiet that at idle, I can't hear it standing next to it.
It's a mouse. It's
Good job.
gone from a growler to an anti-growler. I don't know.
Instead of putting it in the Doka with the growler and waiting to see what the pieces look like in the end, we decided to make one good one and put in the Doka and go ahead and take it apart and see what was inside of it. And I'm glad we did. I learned a lot. Did you?
I did, yeah. I took some knowledge that we gained from an earlier drive unit escapade of swapping inverters out. We did that one kind of out of necessity because we had a broken case.
Yes.
So we took the knowledge that we learned from that one and applied it to this one.
And you actually changed the whole inverter.
Yeah, well, you know what?
So this was our growler inverter,
Yeah.
but put in the other.
Yes, there you go. In case nobody's seen what an inverter looks like. This was the faulty inverter, the one that would only do reverse speeds, is that right?
Yep, even in forward.
So
Now,
this was the bad one.
While he's got that up here, an inverter, of course, takes our battery voltage and so forth, converts it into a three-phase output.
Yep.
There's our three phases.
Yep.
That goes to the motor. And we can vary that frequency of that and the amplitude of that to control our motor speed and power. We do that with IGBTs. Right here are three metal tubes that have two ports in them. And those metal tubes are the heat sinks for the insulated gate bipolar transistor, IGBTs, that we use as power switches to make those waveforms.
Okay.
And the problem is they have some resistance when they're on, and that causes them to produce some heat.
Sure, more amperage through more resistance is more
heat.
heat.
And when you're doing 1,000 amps at 400 volts, a very small amount of waste energy puts off a lot of heat.
Sure, yeah.
And so these are the heat sinks, and they're actually metal tubes that the heat sink plate on the IGBT is physically mounted to and adhered to with a thermal
Like
grease
paste, yeah, sure.
to ensure good heat transfer. And in the case of the Tesla, of course, we run coolant through that. And therein lies the tale. Let's take a look at some other things that Bill found inside a Tesla drive unit. I was fascinated. So, in taking this system apart, we found out a number of things. We've known that this is the input for coolant. And so you pump coolant through there, and it goes into this end piece. This is an encoder. It's actually an inductive pickup, but the encoder gives our inverter position information for the motor. All AC induction motors kind of need to know where they're at in order to tell it where it's going. And so there's various schemes to do that. I was enthralled with this particular scheme because here is a very solid tooth gear. Encoders go bad a lot. Mm-hmm. This is a very solid tooth gear that's on the end of the rotor shaft, and a very solid, but also probably pretty commonly available, if I could find a part number for it, pickup. This is just an inductive pickup, like the one we used on the Escalade to pick up the ring. And so that's our encoder. More importantly, this is a distribution block for fluid. And how does this flow, Bill?
Well, as you said,
we come in here,
come in through there, mm-hmm. and then the fluid has a choice. It can either go north or south.
That's right. I don't know if you can see it. There's almost like a little ridge in there that divides
it. It's like a little ramp. Make it easier to decide. Yeah.
And what are the two directions?
Well, if it decides to go up, let's call it up. Up. It comes into the rotor via this tube. It goes
through this tube
and out this tube to the inside of the rotor.
And if it goes down,
it comes out this way, going into the bottom of this end cap, end plate, into the bottom of the stator.
The case and the winding.
That's right, wrapping around it.
And it goes completely through the outside of the motor.
Yes.
And then where does it go?
It goes through the top of the case. We got one kind of blown up here a little bit. So it goes through the top of the motor, through here, into this hole. From that hole, we've got some little arrows on there.
Yeah.
Comes around this way and through all the IGBT.
No, it goes through 3 of them. And then the return side of the IGBT thing goes through the other 3.
Yep.
And that goes out here to where?
It comes out to the front plate. Yeah, which you would see it more like that, and then it can go out to the radiator. Yep.
But this front plate, would you show them the nature of that baffled system? Is like a heat exchanger for the e-gear drive.
Yep.
Or for the gear drive.
For the gear drive, yep.
And we have a tube here that externally goes across from the top of this unit to here, and it comes in here.
Yep. It would go across that tube on this end, across a tube over to here, across the transmission again, which would be through this hole here, across the transmission, and then out.
And that, well, no, it has to flow down through all these baffles.
Little heat sinks.
Heat fins, and combine with the output of the
that's right.
Inverter coolant, and thence out our little, you had it on that plate.
Yeah, to the outlet.
A hookup, a bar thing.
Little fitting there.
Fitting to our coolant system.
That's right, to the radiator.
So that's the cooling. Now, the interesting thing about that is we go through this tube down into the rotor, and then we come back. This rotor, the fluid goes down the middle of it. The rotor sits in here, and and it just terminates. The tube is not as deep as the tube it sits in,
Right.
which is larger diameter, and that comes back and seats here with kind of an O-ring, and so the fluid goes through the rotor and back here and out the top, which is where this external device is connected, and thence over to the thing. And so our fluid goes two directions in a way I did not really understand. One is in the tube, into the center of the rotor, back out the rotor, across here, and to our heatsink plate on the transmission. The alternate route is through the stator, across the top, and into the inverter, and out right at where our outlet is.
Right.
And so I never did quite understand that fluid flow. But that is kind of amazing. Where in all of this did the growl come from?
Well, there were some theories, weren't there? We had a couple theories going about the inverter might have been the problem, maybe a phase out of phase.
Well, we put the inverter on the other thing, and it's deadly silent. I can't even hear it with my hand on it.
So we proved that to not be the problem. It was not the inverter. But it could have been, but it wasn't. The other thing, only really other choice is a bearing, isn't it?
Well, could be in the gearbox.
Could have been the gearbox, sure. Could have been some gears.
And some gears. Of course, we replaced the differential with a quaif. And that's all brand new stuff with brand new bearings.
Yeah, and I checked it all out when we put it back together, and everything looked from inspection to be fine for the gears.
The other bearing in there is a, you can see it down in the hole. It's actually a socket for the splined end of the rotor, and then that has a small gear on the end of it.
Right.
That connects with, what do you call the gear?
A pinion gear.
A pinion gear?
Yep. It goes from the pinion to a larger ring gear to a smaller pinion to another ring gear, and then it goes out.
Okay.
Yeah.
So none of those gears look bad.
The gears looked fine, yeah.
Their bearings turned and were fine.
Sure enough.
Well, that brings us back to the rotor. Let's do a little experiment.
All right.
Bill, here's our rotor.
It's beautiful.
And it has these nice bearings. This is, I want to put this on a desk or something.
it's desk
Work of
jewelry.
art.
Yeah, it's lovely.
What a lovely thing, and it's so smooth. How can we check this out for sound?
Well, you can spin it. You can try and spin it with your hands, but you got to be careful because that is sharp.
Is it?
I don't think this was ever intended to be spun by hand because it's pretty sharp. Or
I'm feeling a little vibration.
There's a little bit. I can kind of hear it, but it's not very loud.
No, it's not.
How can we make it spin faster?
Can we make that spin faster?
I bet we can. I have devised a very...
You have a plan.
Got my favorite DeWalt drill, a little thingy here. Let's see if we can't get some speed going. You tell me when to stop, because we can go all day.
Go all day. All right, let's remove the drill. What is that growling noise?
It's awful.
That's horrible.
It sounds just like it did when it was in the other transmission.
Man. This bearing feels fine.
Yeah.
All we have on the other end is another bearing.
That's right.
And the encoder ring.
Yeah. The encoder ring's not making noise. Must be that bearing, huh? I think we found the problem. We found our growl.
It must be the bearing on the far end.
I guess there was just too much load on that bearing, huh? And it just failed?
Why is there any load on it at all? The gears are on the other end.
That's a good point.
It's just holding this in, centered in the stator.
Well, are there any other ways
There's no pressure on it this way. There's no pressure on it this way. This bearing should last 1,000,000 miles.
Well, short of just a bad bearing, is there any other way that a bearing could go wrong?
You know, I don't think they would have installed the bad bearing at the Tesla factory on purpose.
Probably not, no.
In answer to your question, I don't know. However, there is a theory. Now, this comes from a man who sells brushes for a living. There is a company called the Hellwig Brush Company that makes brushes for DC motors. And Tom Brunka from Hellwig has come down several times and given presentations on the very complex world of brushes for DC motors at our little gatherings here at EVTV. A fascinating guy. Has to feel a little butthurt in a world where everybody's going to AC motors.
They don't have brushes.
And they don't need brushes. So what's a 80-year-old family-run company to do? Obviously, they still use DC brush motors and Zamboni machines.
Sure.
And forklifts and so forth.
Our very own drill here has them. So.
But here, this whole EV thing is taking off and everybody's using AC motors. Tom's theory is that the rotor, of course, in an AC induction motor, turns because the current in the static coils actually induce currents in the rotor. And those currents set up a counter field that the main field in the stator can act on. And that's why the motor turns.
Okay.
That's a pretty good theory. It may be a little past theory. That's kind of a fact. Tom's theory is that inducing currents in the rotor, you also induce voltages.
Sure.
Makes sense. Ohm's law kind of requires it. And so we have a voltage in the rotor and a differential between the rotor and the case, which is normally grounded.
Right.
Now, how do you resolve this voltage here and the basically return or reference ground of the case? Well, you have to have some current flow in order for that to resolve itself. And the bearings are not a very high resistance path.
Metal to metal contact.
Metal balls, metal rim races. There's some lubricant in there, but
that's where I'd go if I was an electron.
That if I was on a rotor and wanted a path to ground, I kind of have two bearings to pick from.
Yes, you do.
Don't I?
You do. Yep.
And so apparently this one wasn't the one picked, but the other one may have, and those currents could cause erosion of the bearings and premature failure.
Sure.
Now here's where the theory gets to be kind of cool. Tom mentioned that there were things he couldn't tell me about Tesla.
Secrets.
Secret stuff.
Secret.
So imagine Bill's surprise. He actually caught this and pointed it out to me. If you reach into the stator and reach back and put your finger inside of the bearing, which turns just toward you on the inside, it's kind of a feathery feeling thing.
Got some little hairs, hasn't it?
Like hairs.
Yeah, roughly. It'd be roughly about here, wouldn't it? Just on the other side of where this sits, it'd be about right here.
Here?
Yeah.
Yeah.
What do you suppose that does? Just kind of keeps it clean?
Probably is a Tom Brunka grounding brush that they must have developed for Tesla.
Oh, in fact, we put an ohm meter on it, didn't we, on the little hairs?
Yes, the hairs are actually conductive.
They are, yep.
And so our theory, and we don't know, is that there is a brush in there intended to leak off voltages in the rotor to the case, bypassing the brushes. Still not known and unclear is why they didn't do the job.
Well, they're kind of dark, aren't they? They're not. If one had imagined that originally they were sort of a silver color, but now they're sort of darkened, maybe they weren't up to the task. They got a little too much resistance, possibly.
You know, I can't go there because Tom's brushes are any kind of color. They use a lot of exotic materials. They say it's a carbon brush. It's not a carbon brush. His grounding brushes, I was told, was some sort of a silver compound. It's not silver. They're kind of advanced composites. I don't know what's in them or what color they're supposed to be.
Okay.
Or how long they are, or any of it. But I was delighted and surprised to find a very clear bearing in there that has no bearing on anything. It's simply a brush to contact the shaft of this rotor and connect it apparently to the case.
They seem to have thought of everything.
But we're left with a rotor that, aside from being a very delightful desk decoration, probably has a bad bearing in it. And by bad, it's probably not anything we could take this apart and see, but I doubt it's anything you can see. It's just eroded surfaces of balls and races that the thing turns fine, makes full power. It's just noisy as hell.
Yeah.
And so may have nothing to do with the Tesla drive unit failures, but it's an interesting failure nonetheless.
Very interesting.
And so that's kind of what we've learned about the rotor and our ground noise. It was apparently, I'm satisfied from the tone of it and everything.
Sure.
That with your drill that was. Took a turkey roaster to amplify that a little bit. But it's pretty clear that that's the same tone that we got in the growler.
Yes.
And the only part left here is the bearing for the rotor. And it's not the kind of bearing that would bear a lot of wear.
There's no load on it.
Right. It doesn't really have any thrust at all.
Just the weight of the rotor, which isn't that much.
Right.
Yeah.
And so I'm a little lost as to how that bearing went bad in obviously a young motor. But there's our observations. So in the process of recombining two drive units, one, we got a good, very quiet, probably the quietest one we've ever had.
Pretty nice.
Drive unit.
Yeah.
With a quaif thing. And your new stub axles.
Yep.
Which are thanks to Randy Lee. I had some made in China, but Randy Lee, I thought, was a viewer who did machining at home, and he offered to help us.
Yeah.
As it turns out, he is the principal in a company in Toronto, whose name I forget, but Bill is going to look up for us, and I'll put it in the video. In Toronto, who actually does a lot of precision engineering level machine work for a couple of large clients up there. The nature of it is he has too much work and then not enough, but has two very good customers who keep him busy most of the year. But he jumped in and made us some of these, and they're just a lot nicer than the ones from China. And so that's what we're actually going to use in the
Doka.
Doka, and he did it at a price pretty much right in between two Chinese suppliers.
Absolutely, and on a tactile level, just feeling it, what he made is much better than...
Bill likes it a lot.
I like it a lot better.
That's what we're going to put in.
He did a great job.
And so you have a drive unit ready to go in a Doka that's increasingly approaching something we could drive if you'll put that motor in. I've kind of stopped him for the last week while we did some other things and wanted to film this to explain a couple of things we learned. One, the source of the noise, but two, I've never had a clear mental image of how this fluid system works.
It was always a little vague, wasn't it? Going in one side, not really sure. Does it go through the inverter
All
first?
the explanations, you know, I can Google anything in the world and get an endless supply of information, but anything I Google about Tesla, I just get like dead silence. It's just, and then there'll be some stuff on Tesla Motors Clubs where people are just ranting, raving nonsense that nothing could work that way, but they've got a theory.
Yeah.
And so the information has been a little bit sparse. I actually have one viewer who was proposing to cut this and make 2 loops on the assumption that one side was the inverter and one side was the rotor. Let me disabuse you of that notion. This is entirely rotor. And it simply moves it from this one to the motor into this heat sink plate on the transmission, on the gearbox. And that's its purpose. It's entirely rotor. Stator and inverter are on a separate circuit. I'm assuming the stator has a lot more mass, and so while it does absorb heat, it's not quite the same level as the rotor, and is sufficiently cool in their mind that then it can be run through the inverter and literally right out of the inverter to our output.
Yes.
So we have 2 separate paths for coolant. Again, I think it's awkward to have the motor, even just the stator, on the same circuit with the inverter. And Tesla has a reputation of overheating on race day. It performs admirably, and after a few laps, it just goes into current mode because of
it just gets too hot.
Temperature. My suspicion is that could be overcome with larger heat exchangers, bigger fans. I don't really understand cooling. Bill says more pump is sometimes not good.
Yeah,
less pump.
Sometimes too much flow over a hot surface doesn't allow enough time for the heat to transfer.
But I think that cooling could be tuned for some performance.
Sure.
Given enough heat sink and fan and so forth.
Yes.
But it's not something we could easily separate. It simply doesn't lend itself to that.
No.
But I now understand the flow of coolant
It's
through
elegant.
the device. And again, every time we crack this nut, I go away, palm to forehead. Man, these guys are pretty sharp.
Yeah, especially with the little brushes. That was pretty cool to find that.
I thought I knew something they didn't.
No, they were there.
Of course, I do know about gearbox lubricants that are conductive.
Do you?
I actually sent an email to Tesla several months ago about that. Never got a reply.
Well, why would you want that?
Because the end of the rotor has a gear on it, and that's in a gearbox full of gears, and with the proper conductive lubricant, could discharge currents.
Could find ground that way.
That way.
There you go.
But apparently they don't feel they need to. I have a rotor indicating maybe they do need something, and that's basically the route to the million-mile motor is iteration. And but I'm in awe of this drive unit, the way it's put together, the thought that's gone into it. This is an amazing piece of engineering, any way you cut it. And I'm in love with the damn things. I may just buy them all, make them all work, and just pile them up here in the room and listen to them turn.
We're going to need another intervention.
Yeah, possibly. Stay with us. Just a short segment. I don't actually have anything to show yet and nothing to announce, but we are in a frenzy of Tesla component reverse engineering. And, you know, a little knowledge picked up from an inverter can lead to some breakthroughs in the battery, and a little breakthrough in the battery and some reverse engineering there can lead to some other things. And so our knowledge base is kind of growing. I, again, am struck by how just a simple Google entry for something like a Tesla charger can bring up such a total lack of information combined with a lot of misinformation. And it's kind of striking. This is a Tesla onboard charger. When Tesla came out, you had your choice of one or two of these. They were each 10 kilowatt chargers, and they're isolated so they can be used in conjunction to charge your battery. This is the new and improved Gen 2 version 11 kilowatt charger. And these chargers are kind of interesting to me. For one thing, we're accustomed to typically in an electric vehicle a 3 kilowatt charger. A 30 kilowatt battery would take about 10 hours to charge. Of course, if you tried to charge your 85 kilowatt Tesla at 3 kilowatts, that's about 30 hours, which nobody wants to wait a day and a half to drive their car. So Tesla naturally put in a larger charger of 10 kilowatts, and in fact, to improve that matter, offered as an option originally 2 of them, and they're located under the back seat. Kind of in between a high voltage junction box, which I have one here, that has some contactors and connectors. You can see it's got a port on each side to accommodate 2 of them. And so that's how they're connected. As I said, we're accustomed to 3 kilowatt chargers. Wouldn't it be nice to have a 10 kilowatt charger? You could put in an EV. And really at not much more expense, because these are boat anchors, essentially. Nobody knows how to work them or even what's inside of them. I buy them on eBay for $500 or $600 a piece, and by far the majority of them, after people strip a salvage Tesla, the components that are saleable, go to be shredded and are sold for the metal that's in them. The weight of the metal. And the charger will, of course, in almost all cases, be perfectly operational when it is melted down for the metal that's in it. That seems a crying shame. That said, the Tesla is, of course, a highly integrated device. The battery is integrated with the charger, which is integrated with the master control unit in the vehicle behind your big screen, and the charge port, which is to some degree a smart device in the Tesla. And so it's a little bit of a task to trick this charger into believing it's in a Tesla. And that's basically all of our reverse engineering attempts are of the same ilk. We're trying to convince the device that it's in the car and should operate as if it's in the car while we're faking the signals and circuits. The Tesla Gen 2 we're going to focus on. They had problems with the Gen 1s. They're not as powerful. They had some failures in them, and by all accounts, the Gen 2 is the more capable and improved version. They actually use it in the Tesla supercharger. They were putting 12 of them in for 120 kilowatts. I don't know how many they are using now, but they basically stack them, use 3-phase power. And it's somewhat agnostic as to the power required to power it. It says 85 to 300 volts RMS, 40 to 60 hertz, 48 amp, and single phase, 3-phase. In actual practice, it has a 6-pin Molex connector that pins 1, 3, and 5 are one phase, and pin 2, 4, and 6 are the other for U.S. power. Now understand, you can hook this up to 3-phase power in Europe, or even plug it into the wall for 120 volts. Here in the U.S., we have, here in the shop, it's 240 volts, but in some areas 208, some areas 220. They call it split phase. It's actually 2 phases, 180 degrees out of phase, and a neutral return. And so 1, 3, 5, 2, 4, and 6 are 2 equal phases, and you don't really have a return. We connect the neutral from the wall to a ground strap to the box, and that seems to be effective. We have another connector out which we get high voltage, and that again is 2, 4, and 6, and 1, 3, and 5. And I think 1, 3, and 5 is your negative, and 2, 4, and 6 is your positive polarity. And in order for this to work, it has to be hooked up to a battery output between 50 and 450 volts. Let's see, what does the tag say? Yeah, 50 to 430 volts DC. And this is rated at 45 amps. Understand, we've been charging our Tesla 85 kilowatt pack with a Chevy volt charger that at 348 volts, it'll do about 8 amps. Here they're talking not about the output amperage, but about the input amperage. And so 48 volts at 220 volts at 48 amps is a little under 12 kilowatts. Inside the charger is 3 charger boards that are identical, and they each put out 3.7 kilowatts for 11.1 kilowatts total. And so this modular thing, you have 3 identical chargers in here. In a Tesla supercharger, you have 12 identical these stacked in a rack. And so in this way, they're all doing the same thing, and that is converting AC voltage into a controlled DC voltage with some intelligence to do the constant current, constant voltage charge cycle, where it'll charge at the maximum current it can obtain up to a certain voltage, and then it'll hold that voltage and taper that current down until it gets to a very low value, at which point you're 100% charged. And all that is done by CAN message. We also have 2 control connectors on the end, one 10-pin and one 12-pin. I have a little EVTV Dewey with a familiar green and white twisted pair that goes to the 12-pin. And then we have this J1772 connector. The J1772 has our 2 phases. The neutral is the bottom big pin, and then it has a proximity signal and a control pilot signal. And that proximity and control pilot are actually wired directly to, as I said, we take the 2 big phases and we run it into the AC. The neutral goes to the case, and that leaves us with our control pilot signal and our proximity signal, which is connected to the 12-pin connector. A proximity signal simply contains a 150 volt resistor to ground, basically. So when you plug in your EVSE, knows that you're connected to, or your car knows you're connected to an EVSE when you press the switch to pull the connector, that changes that value. But when it's in and released, it's 150 ohms to ground through the EVSE. And so the charger is looking for that from the EVSE in order to operate. The control pilot signal is a little bit more complicated. It's actually a square wave, ranging from plus 12 volts to minus 12 volts. Some EVSE cheat on that and go plus 12 volts to 0. And that works a good part of the time. It does not work with a Tesla charger. You need a true plus and minus 12 volt square wave. The duty cycle of that square wave indicates to the charger how much current is available, how much power the EVSE will provide. And at some low level, like 5%, kicks the, is basically read as a request for digital communications over the control pilot line. Tesla does accommodate that. That's how the supercharging or chatter mode charging is accomplished. But it's done really controlled by the battery through a fast charge CAN bus of 33.3 kilobit single wire CAN that is then impressed on the control pilot signal. Whenever the control pilot signal goes to 5%, I think, square wave. And then they can communicate to either initiate a supercharging session or a CHAdeMO charging session. We're not too interested in that at the moment, but we may become more so. And finally, the charger, unfortunately, like the battery, monitors the high voltage interlock loop. And so we've had to devise a little voltage divider and 5 volts to go into some of the pins of the control connector to simulate that HVIL loop and some fault signals, or I guess I would say lack of fault signals, so that the charger will charge. This is a 5 volt, 12 volt, 5 volt converter module, 25 watts. I need about 5 milliamps, I think, but right now that's what I had laying around. And a tape to it is a little board. I'll put a photo up here, just very crudely constructed with through-hole resistors to do the divisions necessary for these fault inputs. So that's our physical setup to make the charger work. After that, it's a matter of developing software for the EVTV DUI to enter the proper commands to the charger to initiate charging and to set, like your voltage you want to charge to, the amount of current you want to use from the wall. And it should give me back some CAN messages indicating the current voltage and so forth. Understand that that's going to be pretty basic because it normally gets most of that from the BMS and the battery. And so we may have to look at coupling this with like a IVT, ISA scale IVT current and voltage measuring device or something to really give you full control. I don't know yet. The little 5 volt and resistor divider, once we get all this working in our prototype, will be moved to a shield for the EVTV DUI so that we can dispense with a lot of this and wind up with a DUI, some connectors, and probably inevitably a J1772 connector wired into the charger. So you won't be able to really use this plugging it into a wall terminal unless you have some device to simulate the proximity and control pilot signal. I could put that on the shield, but ultimately we want to connect to a charge station anyway, so we're probably going to kit this with a connector and some cabling to connect to the charger, and then your control harness and an EVTV DUI and the proper software. Have had no success. We aren't charging anything. I just thought I'd show you what I'm working on this week, and we may fail ignominiously and with great embarrassment. Well, it doesn't happen very often. There's usually some way to figure this out. So we're going to keep after it. That's what I'm doing on my summer vacation now that it's spring.
All right, here we are back at the Doka again. Last time we left off, I think I just gave you a brief overview of what we got going on here. The time we were looking at all the electronics, but now we're going to get into the mechanics of it. We've got the new Doka transmission with its inverter and Growling gone, and it's ready to go into the vehicle now. I've told Jack that I can get this thing up here in 15 minutes. I don't know how serious I was about that. I guess we'll find out if I make it or not. But we're going to give it a shot. I got Duncan over on the controls of the lift, and basically what happens is as he lowers the lift, the rear mount of the motor is going to slide into the rear mount of the frame that I got made up, and once that's in, we'll lower the lift back down, and then the front mount will line up with the front bracket that I made up. And then once those two are in, then I can put the side dog link in, and theoretically that'll be it. We'll see how we do, but that's the plan. All right, Dylan, take her down. There's just barely clearance on this lift to get everything through here. I mean, we literally have about an inch on each side of this little plastic water inlet that is, by all accounts, if you break it, you can't find a new one, but we made it, so we're good. So now we're coming down, and I'm just making sure that we're all lined up here. You look good in the back. All right, hold on, Dylan. All right, come down. Come on. All right, come down. And hold on. Okay, come down. Come on down. All right, hold on. So I've got the front mount kind of lined up, and come on down. This is the tricky part, getting the back one in. Come on down and hold it for a second. Okay. Come on down. Come on down. Come on down. Keep on coming. Come on. Come on, come on. And stop. A little bit. All right, now take it up. Give me power. Jack it up. Not down, up.
Yeah, hold on. Trying to figure out.
Push the button on the.
Oh, it's side.
Yep, come on. Go. A little bit more. All right, now let it down a little bit. All right. See what we're doing here. Let it down a little bit. All right, stop. Up some. Down a little bit. Okay. I need a different angle. There we go. All right, let it down a little bit. A little bit more. A little bit more. Oh, up. Just a little bit. Just blip it. Blip it. Okay. Yeah, this is the hard part. This transmission mount is difficult to get in. How did I do this? Another hammer. It's a shame you guys, I don't know if you can see what I was doing there, but I was doing some little Spider-Man thing. It was pretty entertaining. I don't know where my mallet went. It's left to work. All right, come up a little bit. All right, down. Down a little bit. All right, let's see. How do I get in there? Give you a nice little shot of my butt now. All right, let it lift the truck up. All right, lift it up. Take it away, full, all the way. And just like that.
Good show, Bill. Good show.
All the way, take it up. Ta-da! That was not even 15 minutes. All right, stop.
Do you have axles in?
No, I don't have the axles in. No, they're up top. Oh, to get them in, we gotta put it down. They're up. Let it down. Well, that didn't even take 15 minutes. By golly. All right, stop. Yeah, I gotta pack these bearings with grease. But the gist of it is these will just simply go up in place. There's 6 bolts that hold it into the output shaft, the flange on the sort of the drive flange, and then the other bolts just bolt right into into the stub axles that Randy Lee made for us into the Tesla. So I gotta kind of take these apart and and put all this CV joint goo in them first before they're in there permanently, but it's a pretty simple task to do to install them. But that kind of takes care of installing the Tesla drive unit into the Doka. Now it's just a matter of getting everything wired up and getting the other battery pack in there, plugging it all together, and see if we can get it to not make any noise. All right, we're back here with these CV joints. Going to install these up into our newly installed drive unit in the Doka. Before we do that though, these are brand new assemblies, so they come unlubed, and that wouldn't be any good for driving the thing. So each of the CV joints come with their own little accordion tube of goo, and there's really not much to it. You just kind of pull the axle, or pull the CV joint back like that and squirt some goo in there. It's just really messy. Squirt some goo in there and then just do that until it's kind of full. Get that side and scoot it up this way. Get it in this side. Make sure everything is all coated in goo. And squeeze the rest of it in there. That's pretty much all there is to it. Then we'll just kind of, now all I'm doing is using my fingers to smush this stuff into the actual bearings, just to make sure everything's got good lubricant in there. These are going to see quite a bit of force, so we want to make sure that they're all greased up and ready for prime time. Now if I had a rag, that'd be pretty nice. Got to be really careful if you can take these CV joints apart pretty easily. I think we did a video a few months ago about how this is a Rezepa CV joint. The other kind would be a tripod. That's what the Tesla actually uses, but this is a Rezepa joint. We did a little episode of how that works. And if I'm not careful, I could do another episode of how you take one of these apart. So, bleh. Oh, magic. So here we go. That's that one. And then all that goo stays in there by this metal case, which has some, so the bolts will come in from the outside through that case into either the flange on the outside or the stub axle flange, and screw that together, and it'll hold this sort of gold colored cap on it to keep all the stuff in there. But I want to make sure that my holes are lined up. And I'll just kind of drive that cap on there just to hold it on temporary. Like I say, the pressure of those retaining bolts will secure it in there good. So that takes care of that one. We just got to do 3 more. They give you plenty of this stuff in this little tube here, so you can be very generous with it. And you want to use as much of it out of there as you possibly can. There's no reason to not use it. Just squeeze the rest of it in there. There we go. My wife's gonna kill me for getting grease all over this shirt. Probably not. And then like before, I'm gonna put a hole in there and make sure these are all lined up for me. Okay, Dylan, if you want to lift the vehicle up, we'll get this one installed. All right, so here we are underneath the dock. We're going to put in some drive shafts. Basically what's going to happen is, these are the gorgeous stub axles that Randy Lee made for us. I've got one installed in the Tesla drive unit right there. And then you could call it a stub axle on the outboard side of this swing arm. Basically looks just like that on the inside of here. So one side of the axle is going to be installed in that, and then the other one is going to be installed up on the motor. The tricky part is getting these doggone bolts lined up in the hole because it's dark and it's far away. I need light. I need light in here. Can you hold that right there for me? There we go. If I hold my tongue just right, I can get the other one in too. It's important to have your tongue just right. Wouldn't you know it? I did. Side goes up. I got this axle jacked up so I can turn this tire. That way I can get these bolts lined up. Now before we had this locking differential in there, it was kind of easy to just turn the stub axles of the Tesla. But now we've got that locking differential in there. To turn one stub axle, you kind of got to turn the whole doggone motor. And that is not that easy from down here. So, we jack up a tire. Let's try a different one. That's some fine threads, Randy Lee. Nicely done. All right, that's 2 out of 6. That's pretty much how that works. Get the other 6 in there and that'll be it. You're ready to roll. All right, back under the Doka. So what I've done is, since I've got the rest of the bolts installed for the CV joints, I had to kind of take a step back. I realized I didn't put any way of securing those bolts so that they don't back out. So I've installed our famous Nord locks that we like to use around here. I've installed those on each of the 24 bolts that secure the CV joints into the outer and the inner stub axles. And that'll be good. And if we turn the axles, you notice that they do spin together, but they don't spin together in a locked fashion. And the reason for that is because we don't have a locking differential per se, as a torque biasing differential. And the difference being is that there is a little bit of engineered slip in a torque biasing differential. That's what separates it from the kinds that have clutches or, well, not the clutch ones, but the ones that have like a mechanical locking feature to them. We've got an engineered amount of slip so that when you go around a corner, the outer wheel can spin faster than the inner wheel. And that's by design. So that's why we don't have an exact lock when you turn one to the other, but they do both turn when you turn one, so that's what it's supposed to do.
Well, Bill, 15 minutes?
16.7 minutes.
Well, we got into a little bit of grease packing, and
Yeah.
24 bolts is actually a lot of fun.
And they're not easy to get to, bolts either. You got to turn the tire to get to another one, turn it to get to another one. It's kind of time consuming to get to them all.
Well, it isn't that hard.
Nope.
In fact, contrast for me, we have engineered a brace system to hold the Tesla drive unit.
Yes.
And we're using stock axles, nothing special.
Right.
And your stub axles,
Yes.
which we did have to go to 4 or 5 different vendors before we got 3 of them actually to cough stub axles. We're stub axle poor now.
Yeah, we've got a lot.
But as you said, Randy Lee's, man, they were very nice. And so threading into them was pretty easily.
Absolutely, yeah. Very nice. Very, very nice.
And so you've done a build with high performance electric vehicles, AC
76. 76, yeah.
in a Ford Ranger.
Ranger, yeah.
And that involved a adapter plate. And
Yep, I did. Had to buy an adapter plate online. Got that online.
we got all that stuff from us.
I got everything else from you guys,
Everything
yeah.
else, yeah.
Yeah. It's
And
kind of ironic.
And you put all that together. And now you've done the thing for the Tesla drive unit.
Yep.
And the kind of the axle drive type thing, no transmission to speak of.
Right. Sort of direct drive.
Contrast that for me. Level of effort.
Level of effort. As far as making the bracket goes, I would say making the bracket is a little bit more complicated for this because it's a physically bigger thing. For my Ranger, I just had to make a front plate that bolted to the original motor mounts on the frame, you know, just the original rubber motor mounts. So it was just a simple plate with some arms coming off of it. I later had to beef up a bit, but whereas this, it involved sort of making a jig that was formed inside of the original subframe, inside of the original Tesla subframe, made that jig, suspended the jig, did a bunch of measurements, got it in there, and then having that held in place, and then making brackets, making a tube that goes across, welding that to that, and welding all stuff together. So it was a little bit more involved to get this framework up there so we can mount the Tesla in there. Now that it is, removing and replacing this motor, transmission, inverter it's nothing. It's the longest part is those 24 bolts.
So while we didn't make the 15 minutes, now that you've got the axles installed, if we were going to drop the motor, it's 6 bolts on each side. We don't even take the axles out.
Right, we'd leave the axles in the outside and just take them out of the inside and then drop it between the two, yeah.
Have to do something with the high power cables.
Yeah, there'll be, I've got, there's the plus and minus cables coming to the inverter from the batteries. Those will have to be undone, but that's just the 2 bolts in the front where they bolt up to the system, and then they can stay in the inverter. Just drop the motor and inverter with them.
Connectors to our wire harness.
That's right, yep.
Just like we do the subclip.
Yep.
So
yeah, and so to remove the motor from my truck would be more involved because I've got a battery bank that's sitting up there. I'd have to remove all of that mess. I'd have to hoist the engine, hoist the motor up, remove the front mount, undo all the bolts from the transmission, get the motor out, and then I'd have to deal with the clutch and all that stuff. And I still haven't got the transmission out if that's something that I wanted, so I still got to do that too. Whereas this, it's just all in one unit and it just drops down with 3 bolts.
So with our frame, sport frame, the axles and the stub axles, what are my chances of success in getting this thing to drive?
I'd say about as close to 100% as you can.
Yeah.
I'm feeling pretty hopeful.
Sounds good. Let's stay after it.
I can't wait.
Oh, here's one of your special tools. Let me leave our viewers with a thought. If you can't achieve a precision fit with a 12-pound sledge, don't force it.
That's good advice.
Yeah. Stay with us. There'll be more Doka.